So section 5.2, logarithm function and their graphs. So here is the rule for logarithm function. For x greater than 0 and a greater than 0, that means positive numbers. And here's another condition, a not equal to 1. Y equal log to the base a for x. This is a really important rule. Y equal log to the base a to the x. Equal. So this is called the logarithm form. And this one is the exponential form. So to convert from the log form to the exponential form, we just have to move the base to be a base for the y. So you see, that means y is an exponent. We're going to move the base from the log to be a base for the other side, which is the y. So a to the y, and the left from this side is going to be x, because when I move the base, I'm going to cancel the log. So when you move the base, you're going to cancel the log, and the left here is just the x. And you're going to do the same thing. If you have the exponential form and you need to write down the log form, you're just going to bring back the base, and you have to write down the log. So it's going to be log to the base a to the x. The left here is going to be y as a number, not exponent. We're going to check that when we do the examples. F of x, which is y, the same thing, log a to the base a for x. That's how we're going to say it, log to the function, log the function with the base a. Here's some properties of the logarithms. Always log to any base, 1, 2, 5, 6, not 1, 5, 6, 700 million to the 1 always equals 0. Log the base and the number exactly the same, like log 5, the base 5 for the 5 is going to be equal 1. Now, here's another rule. Log to the base a to the x. A to the x equal x. That means the base and the number exactly the same thing. So the result is going to be just the number on the exponents here, which is x. The same thing for this rule. If you have a number with the base log, sorry, with exponents log, with the base a to the x, the result is going to be just the x. So these are really important rules, and we're going to check that on section 5.4, how we're going to find this rule. Rule number 4, log to the base a to the x. This is also really important to find the solution. Log to the base a to the x, log to the base a to the y. If you have log to the both sides, that means x equal y. This is 1-to-1 rule. And also, if you have x equal y, you can take log to the both sides. The common log, which is a log to the base 10. So if you see just log by itself, for the x, that means the base equal 10. This is the common log. So the graph of logarithm function. So here is the logarithm function f of x equal log to the base a to the x, and a greater than 1. Always the domain from 0 to infinity. The range from negative infinity to positive infinity. X-intercept 0, 1, and vertical asymptote x equals 0. X equals 0. This information is going to change. It depends about how we're going to get the function. And we will see some of these graphs. They're going to ask you to find the x-intercept, to find the vertical asymptote, and I'm going to show you how you're going to find it. The natural logarithm function, which is ln, ln. If you check the calculator, you will see a function ln. This is the natural logarithm. F of x equal. So if you have a log function with the base e, the exponential function, the exponential here. Also, if you check the calculator, you will see just e by itself. So log to the base e for the x and x greater than 0, always you can change this one to the ln, which is the natural logarithm. So f of x equal ln to the x. The domain for this function always from 0 to infinity. That means you can't take negative number. Also, you can't take 0 because it's going to tell you when you plug in x equals 0 or x equal negative number, it's not a real number. The properties for this natural log is ln always, ln to the 1 equals 0. Ln to the e equal 1. That means every time when you see ln e, you can cancel it. That's what I'm going to do. Why? Because ln times e with this rule equal 1. That's what I'm going to do. I'm going to tell you I'm going to cancel these two, which is mean because ln times e equal 1. Ln e to the x, the same thing. Ln e to the x. You can just say cancel these. The left is just x, not as exponents. So the left here is going to be x is not an exponent. And there is another rule we're going to learn that it's the power rule because we're going to move the x here. So it can be x times 1 ln e equal 1. X times 1 is going to be equal to x. I'm going to learn that next section, which is called the power rule. Here is one-to-one rule. Also, this is important to find the solution. Always we're going to take, if you have ln x equal ln y, that means x equal y. And the same thing, if you have x equal y and you need to find the solution, you can take ln to the both sides. So the one-to-one rule is really important. We're gonna use it to find the solution. If they ask you to solve this natural log equations or solve the equations with the ln. So let's start with example 4, determining the inverse properties of the log, which is log to the base a, ax equal x. The inverse for this one is going to be a to the log ax equal x, which is on the first page. This one. Now, the one-to-one property of natural logarithm state ln x equal ln y. That means x is going to be equal y. So you're just going to say here x equal y. The domain of the natural, check here. They're not going to tell you is like interval notation. Positive rational numbers, positive real numbers, negative, positive irrational numbers. So you're going to choose positive real numbers because from 0 to infinity, that means only the positive real number. Now with example 6, we did 6. Example 7, we have the log form and we need to write down the exponential form. Okay, and they give you an example about that. Let's check how we're going to solve this one. We have a rule. It says every time when you have log, so here's the rule, y equal log to the base a to the x. This is the log form. Keep in your mind, this is the log form. To write down the exponential form, I'm going to move the a is going to be base to the y. So a to the exponent y equal, cancel the log. The left here is just the x. So here is the rule always we're going to use. So if you check example 7, we have it's written the opposite thing. It's written like log to the base a to the x, which is the same thing, equal y. So don't confuse yourself. It's the same thing. We're going to move the base from here to be base of the y. So here it's going to be a to the y, and here the left is just x. So the same thing, you can just flip it or switch these two. So log to the base 6 to the 36. Log, this is example 7, to the base 2 to the 36 equal to the base 6, not 2, equal 2. So this is the log form. I need to write down the exponential form. So what I'm going to do, I'm going to move the base from here to be base to the other side. That means this one is going to be equal 6 squared. The left on this side is 36. So if you check now, 36 is the same thing, 6 squared, because 6 squared is 6 times 6 is going to be 36. So that's the solution for this example. Example 8 is going to be log to the base 7, 1 over 49 equal negative 2. The same thing, I need to write down the exponential form. So I'm going to move the base from here to be base to the other side. That means on this side, 1 over 49 is going to be equal 7 to the negative 2. That's it for this example. 7 over negative 2, 7 negative 2 is the same thing, 1 over 7 squared, which is 1 over 49. So that means this is the right solution. You can check that later. Example 9, the same thing. We have the log form, log to the base 32, and here is 16 equal 4 over 5. So this is the same thing. That means you're going to move the 32 to the other side. The left here is going to be 16 equal 4 over, 32 is going to be a base. That means 32 to the power 4 over 5. Now, if you check this one, can we simplify? Can we get 32 to the power 4 over 5 equals 16? This is a radical, and this one is the exponent. If you can't check that in the calculator, plug in everything exactly is going to be 16. But let's check that without calculator. So without calculator, you're going to say that 32 to the power 4 over 5 is the same thing, 32 to the power 4 as exponents and the fifth rule of 35. Plug in this one in the calculator. Let's check how it's going to be. 32, like just gonna say 32 to the power 4 is going to be the fifth rule of 104,8,576. Then take the fifth rule for this one. So you're gonna go to the math, the nth root, which is 5 to the number 104,8,576. And it's going to be 16. So 16 equals 16. So that's, if you want to just plug in right away to make sure this is right, but this is the way to convert from the log form to the exponential form. So let's plug in also 8, which is 1 over 49. I have to submit that. to make sure it's right, to the power -2. For example 10, we're going to do the opposite thing. We're going to get the exponential form, and they ask you to write down the log form. So this is the rule always you're going to use when you convert from log form to the exponential form. And that's what we're going to do with example 10. Example 10, we have the exponential rule, and we have 3 to the power 3 equal 27. They don't ask you to, is that right or not? They ask you to write down the log form. So look, this one is exactly the same thing here. This is the 3, and here is the y, and here is 27. So I'm going to write down this. If you want to use this one, which is exactly the same thing, flip these two numbers. You can say 27 equal 3 cubed, so you're not going to get confused. Now here is the base. I'm going to bring back the base here. That's mean to write down the log form, I'm going to write down the log. Bring back the base, and here is the 27. The base is a 3. The left is going to be 3, which is this number. So this is the left, and here is the base. We're going to bring back the base. This is A. And you have to write down the log, and here is the 27. So this is the log form. So we're going to type, I'm going to write down the log, which is, I think, functions. Yeah, here's log to the base. So I'm going to write down log to the base 3 to the number 27. 27 here is going to be equal 3. This is the log form for this one. And the same thing, if you use this one, you're going to move the base to the other side, but you have to write down the log here. For the next one, we have, for example, 11. We have 4 to the -3 equal 1/64. So this is the x, and here is this is the x. Here is the number, and here is the exponent. This is the base. So that's mean if I want to use this rule, I'm going to move the base to the other side. So when I move the base, the left here just -3. That's mean -3 is going to be equal. Here's the log, and here's the x, and the base is 4. That's mean log to the base 4, 1/64 is going to be -3. If you want to switch these and work like example 10, is going to be the same result. So don't worry about how you're going to work on it. The main thing, you just have to move the base to the other side for the log. 4 is going to be a base to the log, and here is the x. The left from this side is just the exponent, which is -3. So I'm going to type here -3 equal. Here is the functions, log to the base 4, and x here is going to be 1/64. 1/64. That's it for this one. To find the base, log to the base in the calculator, you're going to click on math. There is math here. So click on the math, scroll down, and you see the last one is log base. So when you click on it, you see it's going to be log to the base. So for this example, I'm going to put the base 32, and I'm going to put the x 16. But they're going to say, okay, when I click enter, it's going to be 0.8. But I have here 4/5. 4 divided by 5 is going to be 0.8. That means this is 0.8. This side is also 0.8. So math, scroll down, log to the base. This is the log to the base. If you just want to use log to the base 10, you're going to click here. There is log here by itself. That means this is the common log. You see there is no base. That means the base is 10. It's a common log. So you don't have to say log to the base 10 for the x. Just use this log. Let's go to example 12. We're going to do the same thing. So example 12 is log, or no, not log, it's 55 to the exponent 0 equal 1. This is the exponential form. So I'm going to write down the log form. I'm going to move the base. That means the left here is 0 equal log to the base 55 for the 1. So we're going to plug in this one in this function. That means how much is going to be the result. They're telling you here log to the base, the common log, there is no base. So this is easier. I'm going just to use log to the base 1/2. That means 0.5. And the result is going to be negative 0.3010. Round to 3 decimal places. So 301. So I'm going to say negative 0.301. 3 decimal places. That's it for this example. The same thing with example 18. We're just going to plug in f of x equal log to the base x, to the x, the common log. That's mean I'm going to say here is the common log. And I'm going to type 92.25, 92.25, close the parentheses, enter. So it's going to be 1.9649, 3 decimal places. So 96, here's 9, so it's going to be 5. So it's going to be 1.965. If you look to example 19, they ask you to use the properties of logarithm. So let's go back to the properties. The properties of logarithm here. Log to the base, exactly the same number. Here's the base and here is the number, exactly the same thing. That means the result here equal 1. That's it for this one. If you look to 20, I told you log to any base, log to any base equal for the 1 equals 0. So log to base 4.5 to the 1. Always the result is going to be equal 0. So I'm just using the properties. Next example, use the properties. 5 to the log base 5, 8. Which one's similar to this one? 5 to the exponents, and in the exponents there is log to the base 5 to the number 8. So the result is going to be x. And how much x here is 8. So that's our result. You're just going to type 8. That's it for this example. So you have to know these properties because make everything easier for you. With example 22, 23, and I think 24, they ask you use one-to-one property to find the value of x. I think just a 22, 24, 22, 23. Now, this is important. We have to use the one-to-one property. The one-to-one property, log to the base a equal log to the base a to the y, xy, that means x equal y. The same thing for this property if there is no base, because the common base, that means the base equal 10. So if you look to example 22, there is no base, that means this is the common base. So I can use this property. So I'm going to say, for example, 22, we have log to the to 11, there is no base, equal log to the x squared plus 7. So now x, log to the x equal log to the y. That means x equal y. So by one-to-one property, that means 11 equal x squared plus 7. In this case, I need to solve this one. So I'm going to say minus 7 from both sides. Cancel here. So x squared is going to be equal 4. Take the square root for both sides. That means x is going to be equal to plus or minus 2. In this case, we have two values. We have x equal 2 and we have x equal negative 2. So this is the value of x. For example, 22, negative 2, comma, and 2. That's it for this example. I'm just using one-to-one property to find the value of x. For example, 23 is going to be the same thing. It's telling you use one-to-one property to find the solution. So log to the x squared plus 6x, x squared plus 6x equal log to the base 27. Log to the x equal log to the y. So by using one-to-one property, x squared plus 6x is going to be equal 27. Now I need to solve this one. So I'm going to move the 27 to this side. That means x squared is going to plus 6x minus 27 is going to be equal 0. Now I need to solve this one. So I'm going to open two parentheses, equals 0, x, 27, I'm going to say 3 times 9. So I'm going to put 9, 3, plus, minus. Let's check 9x, negative 3x. Combine these together is going to be 6x. That means this is the right solution. So we have x plus 9 equals 0, and x minus 3 is going to be 0. That means x is going to be equal negative 9, and x is going to be equal 3. So in this case, for example, 23, we have negative 9, comma 3. So the first thing we need to find the domain. So if you look to this example, it's log to the base 4 to the x. So example 24. It's log, and it's telling you f of x. So f of x equal log to the base 4 to the x. It's exactly like the general form of the logarithm. You see the general form, log to the base a to the x and a equal greater than 1. So our function exactly. So the domain from 0 to infinity, the range negative infinity to infinity, the x-intercept 0, 1, and the vertical asymptote x equals 0. That means x equals 0. So that make everything easier for you. So the domain is going to be from 0 to infinity. And the range, negative infinity to positive infinity. X-intercept is going to be 0, 1. And vertical asymptote is going to be x equal 0. So you see everything easier for you. If you want to check that, let's check by graphing. So when we graph, we're going to click on the Y, math, scroll down, look to the base. The base is 4, and we're going to type here just X, enter. No, we have to click graph. Check the graph. The graph is look like this. We have only one X-intercept. The graph ain't until the 0, because when you plug in 0, the result is going to be not real number. So our graph is going to be stop until the 0. That's mean the domain from the 0 to infinity parentheses, because we can't include the 0. That's mean the number after the 0, which is 0.00001. The number after the 0. So we can't figure out how much the number. So we're going to start writing down from the 0 to infinity. But that means not include the 0, because it's open parentheses. So we can type this information. They're telling you the domain is going to be from negative infinity to infinity. From 0 to infinity to, how are we going to find the symbols? I think, yes. And the x-intercept is 1, 0. Why I type 0, 1? I think there's something wrong here. You have to fix it also with the information. It's 1, 0. It's x-intercept. The same thing here. Sorry for that. This is, you have to fix this one, because this is y-intercept, and there is no y-intercept. It's 0, 1 as an x-intercept. 0, 1. Okay. So the x-intercept here is 1, 0. Vertical asymptote x equals 0. And you can check that the graph is going to be this one. You can't say this one, because this is also the x-intercept here as 1, 0. But the graph, it's not going down. It's end until here. That's why we have to choose this one. The graph is undefined, it's not going to go down, it's going to stop until here, before the negative 5. So we're going to choose this one. Let's check this one and go to the next example, example 26. 25. We're going to do exactly the same thing with the next example. Example 25. I think 25 and 26. These are two important examples. So let's check with example 25. How to find this information. The first thing, function is going to be from 0 to infinity. Is exactly like the previous one. So our domain is going to be from 0 to infinity. The x-intercept, you're going to let y equal 0. That means 0 is going to be equal negative log to the base 2 to the x plus 4. You see, that's different. So now we're going to do the same thing, but this is negative. I'm going to move the negative 4 to the other side. Cancel here. So negative 4 is going to be equal negative log to the base 2 to the x. Now divide both sides by negative 1. So 4, let's say here, divide by negative 1. 4 is going to be equal log to base 2 to the x. Now this is the log form. I'm going to convert to the exponential form. So move the base here is going to be 2 to the power 4 equal x. That means x is going to be equal 2 to the power 4. It's mean 2 times 2 times 2 times 2, 4 times. It's going to be 16. That means our x-intercept is 0, 16, and 0. For the vertical asymptote, is going to be, for this function, it's exactly like the previous example. The vertical asymptote here, just when x equals 0. Vertical asymptote is going to be x equals 0. So this is because it's not going to be a real number. The function is undefined when x equals 0. So we're going to change these. And that's what I did wrong. I put parentheses. I consider x plus 4 as an angle for this one, which is wrong. And here 16, comma 0. And for the vertical asymptote, x equals 0. Now let's check this one. Just look to the graph, because if you look to these 4 options, you're not going to see the x-intercept because it's until 16, and 16 is going to be here. The graph is just showing you until 10. So in this case, vertical asymptote equals 0, which is the function is not defined here, the same thing here, and here, and here. In this case, you have to take 2 numbers and plug in these 2 numbers in the function, or you're just going to make sure sketch the graph by using the calculator, which is this one is going to be the right option, this one. Because you can tell you have 2 options. Here's the vertical asymptote, but the next option, you're going to take 2 points, like 5 is going to be here. It's going to be positive 1, 2, 3, 4, 5. So at the point 5 is going to be 3 or 3 point or 2.9. That means you can take another point, 5, 6, 7, 8, 9 is going to be 1 point something. That means this is the right graph. If you get negative, that means this is wrong. But for sure, this one is going to be the right one. So by taking 2 points from the graph, like you're going to take x, y, take the x like 5 and y, x equal 9, find the y, then after that, you're going to figure out which one is going to be the right graph. By plugging this point, you're going to find which one is the right graph. That's weird. Did I? Oh, I chose the wrong one. Example 26, we're going to do exactly the same thing for 26. So let's solve this one. Find the domain, the x-intercept, and vertical asymptote. They give you the option for the domain, but let's check how we're going to find the domain. The domain, I'm going to plug in the value of x here, which is, if you plug in 0, is going to be negative number. The log for negative number is going to be undefined. So example 26, I can't plug in 0. Let's start, do exactly the same thing to find the domain. I'm going to say x minus 5 equals 0. That means x equals 5. So if I plug in x equals 5 in the function here, it's going to be log to the base 2 to the 0. Log base 2 to the 0 is going to be undefined. Let's write down the function first. So 26, it's h to the x equal log to the base 2 x minus 5. That means I'm going to say x minus 5 equals 0. That means x equals 5. So my domain is going to be from this point That means I can't use 5 to the infinity. From 5 to the infinity. This is going to be the domain. The range is going to be, they didn't ask it for the range. So you have two options. Be careful, it's parentheses, not a bracket. X-intercept, how are we going to find the x-intercept? Exactly like what we did here. To find the x-intercept, we're going to let y equal 0. That means here's y equals 0. No, sorry, here, which is h of x. So 0 is going to be equal log to the base 2 x minus 5. Now, next step, we need to convert this one to the exponential form. So I'm going to move the 2 to the other side. That means this one is going to be equal 0, 2 to the power 0, because this is a base, equal. The left here is just x minus 5, because we're going to cancel the log. 2 to the power 0 equal 1. That means x minus 5. Then you're going to add 5 to the both sides. That means x is going to be equal 6. So our x-intercept is going to be 6 to infinity. Sorry, 6 and 0. This is the x-intercept. To find the vertical asymptote, the function is undefined on this part, which is x equal 5. You're going to say the same thing. X minus 5 equals 0. That means x is going to be equal 5. This is our vertical asymptote, because the function is undefined when x equals 5. So you're going to type here the domain. We choose the domain. The x-intercept is 6 and 0. 6 comma 0. Oops, be careful. 6 and 0 here. And our vertical asymptote is 5. So in this case, let's check which one is going to be the right graph, because we have x-intercept and we have vertical asymptote. So our x-intercept is 6, 0. If you look here, this is not 6, 0. This is not 6, 0. So I'm not going to choose these two graphs. This is 6, 0. And this is also 6, 0. Vertical asymptote, we have x equal 5. So you see there is a vertical asymptote here. And also there's a vertical asymptote here. So we have two options to choose. Without using calculator to find the right graph, you have to take 2 points. If you took 8, like the last thing you have to do without using calculator, you can take 8 and you can take 10. 8 and 10. Plug in these two numbers to find the y. So if the y is negative, that means these 2 points is going to be here. But if the y positive, that means these 2 points is going to be here. You're going to choose this one. For this graph, for this function, if you plug in these two, 8 and 10 is going to be negative. That means the right option or positive. We have to check that. Let's check that. If we plug in 8 here, that means it's going to be math log to the base 2 to the 8. It's going to be 3. Plug in the 10. If you plug in the 10, it's going to be also positive. It's going to be 3.3219. That means if I plug in these two numbers here, the result is going to be positive. In this case, this is the right one, not this one. That's how we're going to choose, by finding the x-intercept, the y-intercept, vertical asymptote to locate which one is going to be the right one. And then the last thing, you have to pick 2 points from the graph, from the x coordinate, and find the y. So example 28 is write the logarithm equations in exponential form. So we need to write down this in exponential form. So be careful on this one. How are we going to write down this in exponential form? So we have the ln, the natural log. We have ln 5/6 equal negative 0.182. So to write down this in exponential form, we already know that just the ln by itself, it's log to the base e, because there is no base here. So I'm going to write down this is log to the base e 5/6 equal negative 0.182. Now to write down the exponential form, that means I have to move the base to the other side. Here is my base, which is the exponential. Cancel the log. That means the left on this side, 5/6 equal e to the exponent 0.182. That's it for this example. That means we're going to choose 5/6, which is 5/6 here, equal e to the exponent this one. So this is the right option. That's it for this example. The same thing with example 29. Example 29, we have ln to the 6 equal 1.792. 1.792. They give you dots here, that means it's a really long number. So the same thing, ln is log to the base e to the 6 equal 1.792. Then we're going to move the exponents to the other side, the base to the other side. The left here is going to be 6 equal e to the 1.792. That's mean we're going to choose 6 equal e to the 1.792. If you look to the rest, everything is not going to match what we got here. So this is example 29. There we go. We have ln to the 1 equals 0. So the ln is going to be log to the base e to the 1 equals 0. Then move the base to the other side. So the left here, 1 is going to be e to the power 0. So that e to the power 0 is going to be equal 1. Example 31, we have to do the opposite thing. See. Example 31, we have to do the opposite thing. So we have e to the negative 3x equal 1/5. How are we going to find which one is the right one here? We can do that one here. Fair one is the exponential to the negative 3x equal 1/5. So you already know that there is a rule, the 1-to-1 rule. It says if ln x equal ln y, that means x is going to be equal y. So that's what I'm going to do here. I'm going to take ln to the both sides. I'm going to say ln to e negative 3x equal ln to 1/5, because this is x and this is y. So I can say this is ln to the x, and here is ln to the y. I'm just using this rule. But I have this side, which is the same thing, ln to the x equal ln to the y. Now let's check the next thing. We already know if you have ln times e is going to be equal 1. That means this one going cancel with this one. So in this case, this side is going to be negative 3x equal ln 1 over 5. Let's check. Do we have this option? It says negative 3x. Here is negative 3x equal ln 1 over 5. We have this option, so we're just going to click on it. If they ask you to find the value of x, you're just going to divide both sides by negative 3. So x is going to be ln 1 over 5 divided by negative 3. So that's it for this example. So 32, we're going to evaluate. We have f of x equal ln x. F of x equal ln x. Evaluate when x equal 14.92. That means f to the 14.92, which is the value of x, equal ln 14.92. Then this one is going to be equal. We're just going to click on the ln 14.92. So it's going to be 270. They ask you to round, I think, yes, 3 decimal places. So it's going to be 2.703. 2.703. So we're just going to type this one because it's evaluate 2.703. The same thing with example 33, that you have different fraction. So let's go to example 34. We're going to solve example 34. 34, use the properties of natural logarithm to simplify the expression. So we need to simplify this one. So if you look to this one, it's a ln to 1 over e squared. We need to simplify this one. What I'm going to do first, we have exponent rule. If you have 1 over a number with positive exponents, you can write it down as a number with negative exponents. So 1 over a number with the positive exponents, I can write down this one equal ln. This is the number with negative exponents. Then we have rule that says if you have ln with the e equal 1, that means you can cancel these equal 1. That means the left here is going to be just the exponent here, which is negative 2. Because this one is equal ln e to the negative 2, which is equal just negative 2. That means we can simplify this one, example 34, to only negative 2. So we can type here negative 2. Example 35 is going to be the graphing. So let's jump. We're going to do exactly the same thing what we did on the graph examples. We're going to find the domain, the x-intercept, and the vector asymptote. Example 36, which is how to solve or use one-to-one property. So let's do example 36, which is len x plus 8 equal len to the 12. Len to x plus 8 equal len 12. That means we're going to use this property. Len x plus len y equal len y is the same thing, x equal y. That's what I'm going to use. That means x here, which is x plus 8 equal y, which is 12. Now, minus 8 from both sides. So x is going to be equal 4. So we're just going to type here x equal 4. With example 37, which is now we have len x squared minus 2x equal len 3. That means x equal y, which is here is the x by using the same property equal 3. Minus 3 from both sides. So it's going to be x squared minus 2x is going minus 3 equals 0. Now we're going to open two parentheses equals 0. Here is x and here is x. Here is a 3 and here is 1 because 3 is only 3 times 1. So put negative here, positive. So it's going to be negative 3x and positive x, which is negative 2x. That means x minus 3 equals 0 and x plus 1 equals 0. So x is going to be equal to 3 and x is going to be equal to negative 1. So we have two solutions here, 3 comma negative 1. Example 38, which is very important examples. Don't feel like it's hard. It's not that much hard because we have the formula. It's telling you the formula is b equal 10 log to base 10 I over 10 to the negative 12. Let's check how we're going to solve this one. B equal, telling you B equal 10 log to the base 10 I divide by 10 to the negative 12. So that's the function. They already gave it to you. They ask you, here's the important thing, the I, which number you're going to plug in here. So if you look to the A, they're telling you determine the number of table of the sounds within, so 1, because they're telling you I is the intensity, which is 1. So we're going to plug in 1 here. That means B is going to be 10 to the log to the base 10, 1 over 10 to the negative 12. So you cannot plug in everything here in the calculator, but what I'm going to do, there is a rule that says 1 over a number with positive exponents is going to be the number with negative exponents. That means if I take the reciprocal for this one, 1 over 10 to the negative 12 is going to be positive 10 to the 12. So here is 12. So this one is easier to work on. That means B is going to be 10 log to the base 10. And here is going to be 10 to the positive 12. Now, there is a rule that says if you have log to the base A to the a to the x, the result is going to be x. This is the log properties. That means just this side, the result is going to be 12. And I have 10 here times 12. That means b is going to be equal 120. I'm using the logarithm properties. So I'm going to type the first one here is 120. B, this, you're going to do the same thing, but now I equal negative 2. So here's B. The same rule is going to be B equal 10 log to the base 10. Here is 10 to the negative 2 divided by 10 to the negative 12. Again, we have another exponent rule. I need to simplify this one. It says if you have a number with the exponent m over the number with exponent n, the same base is going to be the base m minus n. That means here's b is going to be equal 10 to the log to the base 10, and here's going to be 10, m is negative 2, minus n is negative 12. That means b is going to be equal 10 to the log to the 10, and here is going to be 10. Negative 2 plus 12 is going to be 10. We're going to go back, use the same rule here. If you have log to the base a to the x, the result is going to be x. The same base with this number, so the result is going to be x, which is just 10. And here is 10, 10 times 10, so b is going to be equal 100. So we have 100 and we have 120. Here is 100. That's mean from part 8 and part B. Select, they are different. The difference is due to which relationship between these two, due to the logarithm relationship between the number of density, and that's it for this section.